Welcome everyone to the YouTube channel Spark Research. I am Dr. Veer, Assistant Professor in the Department of Electronics and Communication Engineering. It's a pleasure to have you all here. In this session, we will be discussing and solving important questions from GATE 2025, specifically from the subjects of electronics devices and PCB, right? This session is designed to help you understand the concept behind each questions, improve your problem solving skill and gain better clarity on topics that are frequently asked in the GATE examination. So in this session, like before going ahead, let me tell you, GATE isn't cracked in the final year. It's built quietly from your first lecture of your BTech. One concept at a time. Stay consistent now, and your future self will thank you. Okay, let's go ahead. So here is the overview. Before going to talk, let's see the syllabus for this particular course, electronics devices here. You can check it. Mostly the questions may come in the range of the 10 marks. So this is very important topic. Okay, let's take the question. So here is the question. This is a question related to the transformer. So in a circuit transformer, N is to one step down transformer and the diodes are ideal. Diodes are ideal means what? Like it will have the cut-in voltage almost zero and immediately it will have the very high amount of current and the reverse current will be almost zero, right? So this is the current axis and the voltage axis. Okay, so the diodes have no voltage drop in forward biased condition. So here cut-in voltage is suppose almost zero. Okay. If the input voltage that is Vs, here we are applying the Vs, that is equal to how much? 10 sine omega t, and the average value of load voltage which will appear across this resistance RL is already given the average value, that is equal to how much? 2.5 into pi, right? So the value of n, so what is the value of n? That is the question, right? So as per your answer, your options are given as per your answer key. Answer A, that is 4, should be correct. So how can we solve? Before going ahead, let me tell you about the transformer, the basic transformer. V primary divided by V secondary is equal to N primary divided by N secondary. So you can rewrite like V1 by V2 is equal to N1 by N2. So here number of turns, like right side it is given, that is N2, or the Ns is already given how much? Ns is 1 and Np is given your N. So this is the question. You have to find out the N. And input value, that is your V of P is given here, that is your Vs. So this is nothing. This is your tan of sine omega t. And V of S, that you have to calculate. Okay, so not V of X, you have to calculate the V of S that will across, the appear across this. So here this value is already given, that is 2.5 by pi. So now we have to calculate the N, right? Okay, so let's see and solve the questions. So first of all, whenever you are giving any input, so what will be the voltage across this half wave, so that we can find out. So input source is given, okay, and the average load voltage is already given 2.5 by pi in the question itself. These things are given. Primary voltage is, peak voltage is 10 volt, and so half voltage, half wave, like the voltage that will appear across this, how much? So that will be a b, that you can use b1 by b2 equal to n1 by n2. With the help of that equations, if you will put all those values, you will get 10 by twice of n, that is 5 by n, across what? Across this half of rectifier, right? So here you will get that voltage. After getting this voltage, what to do? You have to find out the average. So this is the peak value only. Now you have to find the average. So how will you get the average value? So for since this is a full rectifier, so for full rectifier average, that is VRMS is equal to for IDC, not VRMS. IDC your is equal to VDC is your twice of Vm by pi. This one you have to remember, right? This is valid for average current, that is IDC or VDC. For full rectifier, for half wave rectifier it is Vm by pi. For full rectifier twice of Vm by pi. So put all these values and you will get this value. So Vm is nothing, your V of half that we have already get, that is 5 by n into B. So now put these all values to solve. So in the left side 2.5 by pi already given in the question. This is that is your average value, right? Average load value, that is across this load, okay, terminal. And the calculated with that we have calculated, that is nothing, your twice is your 2, and V half, how will you put the value of V half? That is 5 by n. Here from here only you can put, and then divided by pi, and solve these values, you will get n is equal to 4. So this is the answer. Let's see the detailed calculation. So step 1, first of all find out the voltage across the half wave rectifier, that will be equal to 5 by n using the equation V1 by V2 equal to n1 by n2. All the parameters are given. Then average value across any full wave rectifier is equal to twice of Vm by pi. This is the one simple formula you can remember, otherwise you can also calculate it. This is not a very big deal. Okay, for half wave this is Vm by pi, and for full wave this is twice of Vm by pi. After getting this value you can get the average load value, that is twice of 2.5 by pi. This is already given in our question. So here put the values twice of, like Vm, here it will be twice of Vm by pi, so 2 into, and instead of Vm you can put this 5 by n that we have already calculated, divided by pi, and you can use this expression that has been given. Solve, you will get n is equal to 4. So that is the final answer. Okay, let's take the another question. So in this question, which of the following statement is true for BJT with respect to the DC current gain beta? So what is beta? Beta is equal to nothing, IC divided by IB. So the current which is passing through the collector divided by the base, that is beta. So beta IB is equal to, you can also write IC. So in this question they are asking the something about this beta only. So how can we solve? Let's see the statement. Statement 1, high under high level injection condition in forward active region, like there are the two regions. What are that? Saturation and the active region. So this is your active region and here is the saturation region, so linearly increasing, right? Okay, so beta will decrease with the increase in the magnitude of collector current. So whenever magnitude of IC is increasing, in that case beta is increasing, right? So IC by IB. So if IC is keep on increasing, beta will also keep on increasing for high level injection condition. Yeah, this is true. Under a low level injection condition in forward active mode, when the current at emitter bias junction is dominated by recombination generation process, beta will decrease with increase in the magnitude of collector current. So of course this is not true. Your it will increase, then it will also beta will also increase. So beta will increase with respect to the IC. So this is not true. Beta will be lower when BJT in saturation region compared to the active region. So this is true. For saturation region it will be lesser, for active region it will be higher. For the high value of beta will be lead to the lower value of the collector to emitter breakdown voltage. So this is also true. So let's see the details explanation. So here is the detailed explanation. So under the high value, under the high in level injection, the concentration of injection majority carrier in the base carrier comparable to the majority carrier concentration. This increases the rate of the recombination in the base and reduces injection efficiency, right? And that leads to the beta will decrease if the collector current is increasing. And just opposite to that, beta will actually increase while current collector current is decreasing. So second one is false. Third one is telling like saturation current versus active region, third and fourth. So in that case, what will be happen in the active region? Of course, like you said, beta will be lower compared to the saturation region here. So in active region, the collector base junction is reverse biased, allowing the current to the efficiently sweep across carrier. So the saturation region, both injection are in forward. This causes the collector to emit carriers back into the base, significantly reducing the effective current gain. That is why your beta will be the force in saturation much more lower compared to the active. Okay, so answer is your ACD is correct. Here you can see the detailed explanation as well. So beta will decrease due to the Webster effect in the increased base recombination model, right? And for option B, low level injection. Low level injection, beta decreases as the ideal diffusion current overcomes ideal recombination current. In the saturation region, what will happen? So beta saturation is lower is than compared to the active beta, right? Due to both junction is in forward bias. For breakdown voltage trade-off, your VCE and beta, right? So higher beta loads to the lower VCE breakdown voltage. Okay. So that's all in this session. Before leaving, let me tell you, play today for your health. Stay healthy tomorrow and learn for a lifetime. Thank you.